Domain adaptation is where we train on one kind of data and then deploy the model on a slightly different kind of data. For example, we might train on relatively high-quality labeled photos, like in the ImageNet data set, but then deploy in relatively low-quality photos taken by users in real environments on their cell phones. One solution to this is the domain adversarial networks framework. The basic idea is to establish a two-player game where one player extracts features from the image that are intended to be good for classifying the image accurately, and another player attempts to look at the features and guess which of the two domains the input belonged to. The feature extractor network tries to learn features that are not just good for classification, but also fool the domain predictor network, so that it ends up learning features that are independent of the domain, and the feature quality doesn't degrade when we move to the final domain. This doesn't necessarily work in every domain. I heard a story from Alyosha Efros at Berkeley that he tried to see if this would work if you used the domain of training images and test images. And unfortunately, it did not cause performance on the test images to get better. It caused performance on the training images to get worse. But there is actually one way that you can use domain adversarial learning to perform well at test time. It's called professor forcing. The basic idea is that recurrent neural networks used to generate text are usually trained with a technique called teacher forcing. The training data contains sentences of text presented one word at a time. And the recurrent net is trained to load one word at a time of the training set text and maximize the probability of the next word in the sequence. But at training time, the RNN's predictions are never used as input to the RNN itself. If you read the word adversarial learning and the RNN thought you were going to say adversarial machine learning, the word machine that isn't in the training data never actually gets fed back into the RNN. This means that the RNN does a good job of maximizing the likelihood of the training set, but when you deploy it to generate samples, it might have to generate samples that are very different from anything it saw during the training time. And in longer and longer sequences, it veers further and further from the training data set and starts to produce worse and worse quality of samples. The idea behind professor forcing is to replace teacher forcing with a domain adversarial learning process. The two domains are the domain of running the RNN clamped to the training data and running the RNN in free sampling mode. The hidden units of the RNN are then trained to be statistically indistinguishable between these two domains in order to improve the sample quality of the final model. We can also see that generative adversarial networks can help with domain adaptation by simulating the final domain. For example, GAN, developed at Google Brain, trains in simulation to learn to grasp, for a robot to grasp many different objects. But in the original simulator, there is not very much interesting background behind these objects. In the real world, the background is full of distracting clutter that appears both in the camera and in the depth mask used to guide the arm. GAN is based on training with generative adversarial networks that produce realistic clutter in order to simulate the final deployment domain better during the simulation stage.